So welcome to this course on calculus. So what is calculus? That is the question that we want to ask. What is calculus? And I think the best way to kind of answer this question is to look at what are some of the questions that calculus is trying to answer. So the questions that calculus is trying to answer is going to typically be related to this idea of rate of change. Now, you may or may not have heard of the term rate of change before, but rate of change can be thought of as something along the lines of speed. That would be an example of a rate of change, velocity. Anytime something changes with respect to time or perhaps with respect to another variable as well. So maybe a volume flow rate, that would be another example. So if you're filling up a bathtub, how quickly is that bathtub filling up with water? Maybe your pay rate. So if you work a job, perhaps your hourly pay rate. So all of these are examples of rates of change. And if I were to figure out, well, how do I calculate a rate of change? Well, the answer to the how do I calculate a rate of change question would be just with a simple formula. For example, if I wanted to figure out what my change in position was, I could calculate this by taking my velocity and multiplying it by my change in time. Sometimes we would call this, delta y or we'll say delta s for change in position. And then velocity might be the rate of change, and then this would be delta t. Another way that you might have also seen this is I could rearrange this equation. We could say that velocity is equal to the change in position over change in time. So both of these are valid ways in which we can represent velocity. But there's actually a little bit of a problem here. But to see this, we're going to have to do an example. So let's maybe do a very specific example of how this would work. Is let's say that you were on a highway and you were at mile marker 30. So let's say you start at mile marker 30. And let's say in 2 hours, you are at, we'll say mile marker 200. And I were to ask the question, well, how fast did you go? Well, if you look at the equation that we have up here, delta s over t, the change in position over the change of time, really this is just a slope question. You're going to notice that the relationship between slope and rate of change of time, or rate of change in general, is going to kind of be the same idea. So what we can do here is we can calculate that velocity. So velocity is going to be equal to the change in position. So we're going to take 200 minus 30 and then divide it by the change in time. So 2 hours went by, so we went from 2 to 0. And if we calculate this, we're going to see that this gives us 85 miles per hour. But what is the issue here? The issue is that, well, when you drive on the highway, are you always going 85 miles an hour? Is this constant? And more than likely, the answer is no. Oftentimes, you're going to be speeding up, you're going to be slowing down, you're going to be moving at various speeds along the way. So really, when we say that this is the velocity, this is not really the velocity, but it is the average velocity. So on average, your speed is going to be 85 miles per hour. And this is what's going to be what we're going to call an average rate of change. And going forward, I'm just going to abbreviate this as AROC. Okay? So what does calculus try to do? Well, calculus tries to kind of narrow this down to not necessarily an average velocity, but it actually is trying to figure out something that's happening instantaneously. So if you're driving down the highway and at a particular point in time, you want to know what your exact speed is right then and there, and you look down at your speedometer and you see, oh, I'm going 50 miles an hour right now. That would be an instantaneous rate of change. So the idea is calculus allows us to get an instantaneous rate of change, or something that's known as we'll call it IROC going forward. So I guess, so what is this actually going to look like from a graphical standpoint of view? Well, the idea here is with finding the average rate of change, the goal was, well, if I had a graph, so let's say I have a function f of x, and I have some value x here, we should have noticed above that what we had was a slope type of problem, right? I mean, we should remember that the slope is, something like y2 minus y1 over x2 minus x1. It's kind of the same idea here, okay? So with a function, if I have a particular function, I want to see what's going on over time. So we've got something that looks like that. Then what I can do is I can pick 2 points on here. And if I wanted to find the average rate of change between these 2 points, I would just connect these dots. Okay. Now, if I wanted to instead figure out what an instantaneous rate of change is, well, what would that look like? Well, that's going to be a little bit different because really we're not trying to find an average rate between 2 points at this point in time. Instead, we're actually trying to find what our velocity is at this point right here. So this is going to be this slope. Well, we're going to actually call it the slope of the tangent line. And really all a tangent line is it's just a line that touches the point. It's just a single point. Whereas over here, we would call this a secant line. And it's called secant because it touches at 2 points. So we'll revisit that terminology as we go forward. But this is something that is going to require calculus. And we'll see in the next section that you can't necessarily find this instantaneous rate of change directly from how you would do an average rate of change. You need a little bit more work to deal with that. The other problem is more of the distance problem, okay? So this instantaneous rate of change, this is more of, I should say, this is the theme of what's known as differential calculus. So that's one of the 2 main branches of calculus. The other being integral calculus. And integral calculus instead is going to ask a different question. This time, let's say you know what your speed is over a particular point in time. So maybe let's rephrase the first question that we had. So let's say that you are going to travel 60 miles per hour for 3 hours. And now I ask, well, how far did you go? And, well, we can rearrange that equation. That was actually one of the first equations. So we know that distance is equal to rate times time. So if we take the rate, that's going to be 60 miles an hour. The time is going to be 3 hours, and that's going to be 180 miles. So that's kind of how we can deal with that. But again, this poses the same problem. This assumes here that that rate is actually going to be constant. Again, when you're on the highway, are you always going 60 miles an hour? More often than not, that rate is changing. So what integral calculus does is it actually is trying to figure out what's the total distance that you travel if your rate is actually changing. As a matter of fact, one way to look at this problem from a geometric standpoint is if you have a function. So let's just say I have a function, and let's look at this example up here. If I've got x over here, so this is going to be our time in this example, and this up here is my rate. Well, if my rate is a constant 60 miles per hour, it's just going to be a flat line. And then if I want to know what's happening from 0 to 3 hours, so that's miles per hour, this is 3 hours, well, then the total distance is actually going to be the area. So the area is actually going to be the distance that's traveled. Okay, as a matter of fact, it's the area of a rectangle. So it's a rectangle. And we know that the area is going to be equal to the length times the width. So the area is just 60 times 3. So again, notice that there's an analogy between this geometric problem and the distance, rate, and time problem. But again, well, what happens if the rate is changing? So if the rate is changing, the analogy still holds true. So the question again is, what if the rate is changing? Well, in this particular example, you would have a function that is changing with respect to time, like that. And it would still be the area. But now you're not finding the area of a rectangle, you're finding an area of kind of this arbitrary shape. So finding this area, also known as the area under the curve, that's the topic of integral calculus. So the point is that calculus is going to take some problems that we see from algebra, geometric problems, slope problems, and its job is going to be to figure out solve these more general problems that algebra would not allow us to solve. So we're going to look at how to solve these problems in future videos. Specifically, I'm going to look at the differential calculus, the slope problem first, and we'll look into that and we'll see why algebra is not a sufficient means to deal with that. So that will be on the next video, but I hope that you are excited to learn calculus along with me, and I'll see you next time.